which is an element of F. So this is okay too. What about this? H and T. This is actually omega itself, right? So the complement of omega is empty set, which is a member of this F. So all the elements, if we take any of these, its complement is also a member of this F. So the axiom 2 is satisfied. Then let's check the third axiom. So that says if we take any pair from this F, their union is also a member. Okay. So let's take, you can actually try all pairs like this and this. Let's say this and this, 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 this and this. Okay, but in any case, you can show that they are also a member of F. Okay, for example, let's say if A is empty, then whatever the B is, let's say B is anything from F. Okay, then whatever the B is, this A union B is empty union B, which is B. Because B is an element of F, this union is element of F. So this case, all these cases are okay. Then let's say if A is omega itself, then A union B is A. I mean, that is omega. So omega union B, so B is assumed to be an element of F. So whatever the B is, this union is necessarily omega itself, which is a member of F. So these pairs are okay. So what's left is this pair. Okay. So if A is this and B is this, T, then the union A union B is H union T is HT, which is omega itself. So this is an element of F. So for all these pairs, the axiom 3 is satisfied. Therefore, this collection of subsets of omega is an algebra. Okay? Oh. Okay. Now, regarding axiom 3, so if A and B are elements of F, then their union is an element of F. This can be easily extended into any number of subsets. For example, A1, A2, and so on. Let's say up to AN. If all of them are elements of F, then their union, A1 union, A2 union, up to AN union, then this union is an element of F. So actually, if we assume this, then you can show this. It can be proved very easily. So this is an exercise. By the way, this union of many subsets can be written as this. N A K. Yeah. So this is same as this. So it's just like you write this. Is A1, A2, and so on. Okay, just like you write like this, sigma for summation, you can write union for the union of many sets. Okay. So this algebra is okay uh, when the sample space is finite or countable. But when it becomes uncountable, this algebra, axiom of algebra, is not sufficient for defining probability values. So we extend it a little bit so that the third axiom is a little bit different. So sigma algebra. So by the way, this is called sigma. Sigma. So it's a Greek letter. Lowercase is this and uppercase is this. So it's used for summation, right? So sigma algebra. Algebra. So the axiom is almost the same. One. Okay. Let's see. So we have a sample space. And we have F, collection of subsets of omega sample space. Then this F is called a sigma algebra if it satisfies the following three conditions. Omega is an element of F, and if A is an element of F, then its complement is also an element of F. And 3. So these two are the same as algebra. What's different is the third condition. If A1, A2, and infinitely many subsets are elements of F, then their countable union, infinity here, is an element of F. So the only difference is here. Okay. In algebra, there were only two sets, two elements involved, right? But from this, you could actually derive that the same holds for any finite number of elements, like this. So this one, okay? So actually, so these two are equivalent, but what's important is this is finite, okay? So it's finite number of union, but in the sigma algebra, it's infinite. So this is a very subtle difference, but it makes a big difference later on. But we will not go into the details why it is so. You will, if you want, you can learn this in advanced probability theory in 4th year. Okay. And so if F is an sigma algebra, then elements of this F, so subsets of omega, which are elements of F, they are called measurable sets. So measurable sets. So it sounds like it can be measured by something, right? So by what this can be measured? The answer is it's the probability. So probability can measure the size of these sets. So elements of these are events, and for those events we can define a value of probability. Okay, if a subset of omega does not belong to this sigma algebra, then we do not define probability for that event. Okay. And here's some vocabulary. So let's say we have a sample space. We have a sigma algebra. Well, if this omega is finite or countable, this sigma algebra is not so important. It can be just algebra. So if we have these two, then the pair of these two. So we make a pair. This is called a measurable space. Okay, this is just a name. So if we define a sigma algebra, oh no, for it to be called measurable space, it has to be sigma algebra actually. Okay, sigma algebra. Okay. Well, it may sound too abstract, so let us consider. Okay. Now, in the previous example, this algebra contained all the subsets of omega, but there are some examples of algebra or sigma algebra that is not that does not contain all the subsets. So, for example, let's say if omega can be anything, any set. Let us define a collection of subsets of omega as this: empty set and omega itself. Actually, this is an algebra. This is a sigma algebra also. Okay. Oh, by the way, so we define algebra and sigma algebra. So the difference was the third condition, right? And if F is a sigma algebra, then it is also algebra, but not vice versa. So if sigma algebra, then it is also algebra. But not all algebra are sigma algebra, so this does not hold. Okay? So be careful.